Hello. So in this final part of this chapter, we're going to look at something called binomial estimation. So we've looked at how you could expand brackets of the form x plus a to the power of n. We used the binomial theorem and the coefficients, stuff like that, to work out all the terms of the expansion. So we know how to expand it all, but there's a use for that. And we're going to investigate a particular use of the expansion in this section. So, what I'm going to say is, for an example, I have the bracket x plus what x plus 1 to the power of 10. Now, actually, I want to to the power of 4. Okay, I want to find the expansion of this first of all. Okay, which should be fairly standard. So that's going to be, well, firstly 4 choose 0, and then we're going to have x to the power of 0, then 1 to the power of 4, then we're going to have 4 choose 1, which should then be x to the power of 1, and then 1 to the power of 3, then we're going to have 4 choose 2, x squared, and then 1 to the power of 2 as well, then 4 choose 3, x cubed, 1 to the 1, and then 4 choose 4 lastly, and then x to the 4, and then 1 to the 0. And we can work that all out. So, well, 4 choose 0 is 1, x to 0 is 1, 1 to the 4 is 1, so we get 1 for the first term. The next term is 4 choose 1, which is 4. 4 times x times 1, that's going to be 4x then. Then this next, the x squared term then, 4 choose 2 is 6. 6 times 1 is 1, so we get 6x squared. Then the next term is going to be 4 choose 3, which is 4. X cubed is, well, that's x cubed times 1, so we're going to just get 4x cubed. And so then the last term, 4 choose 4 is 1. X to the 4, 1 to the 0 is also 1, because the power of 0 makes it 1. So overall, then we just get x to the 4. So that's my expansion. Okay, what I'm now going to do is, we can use this expansion, because what I can do is estimate certain numerical values. Okay. Okay, so what if I said then, what if I said I could try to use this to find the value of 9 over 10 to the power of 4. Okay, so hopefully you can notice then that the brackets here are sort of the same, right? They're a bracket raised to the power of 4, but then have x plus 1 inside of here and 9 over 10 here. Well, actually, what if then I put the brackets equal to each other? What if I then said x plus 1 is equal to 9 over 10? If I were to sort of like solve that then x would be minus a tenth, right? Okay. So obviously to find this value then, I could put it in the calculator, but obviously for the sake of, for the purpose of learning and this example, we're not going to do that. And but I want to find a more proper way of finding the value, right? I'm just put it in the calculator. But I can kind of use this expansion then, because if the brackets are the same, when x is minus a tenth, that means I could substitute that into the bracket, into this expansion, sorry, and then that should get me 9 over 10 to the 4, right? Because then x plus 1 to the 4, that's going to equal minus a tenth plus 1 to the 4, which is indeed 9 over 10 to the 4, right? Because 1 minus a tenth is 9 tenths. But then I can use my expansion, because these are all the terms in expansion. So then that'd be 1 plus 4x, that'd be 4 lots of minus a tenth. Add 6x squared, that's 6 minus a tenth all squared. Add 3 minus a tenth cubed. add 4x cubed, so 4 lots of minus a tenth cubed, add minus a tenth, have to squeeze it in here, to the 4, right? If I put that in the calculator then, all that, so 1 add 4 of 4 lots of minus a tenth, add 6 lots of minus a tenth, squared, add 4 lots of minus a tenth cubed, add minus a tenth to the 4, I get 6561 over 10,000. Well, actually, if you were to put that in the calculator, that's equal to 9 over 10 to the 4. Right? So actually, we do get the full proper answer. Okay, cool. So that's what we'll be using our expansions. We can use it in that way to find particular values. Yeah, and that'll be, especially when you look at more types of binomial expansion in year 2, where you can actually go on to find all different types of numbers, including irrationals like root 2. We can use certain binomial expansions to find the approximate value of root 2, which is useful because root 2 is an irrational number that goes on forever. So if we can sort of find sort of an approximate, like finite, proper answer to that value, that it can be quite useful. And for example, with pi as well, people all over the world trying to find all different ways of trying to approximate and find the next few digits of pi. We come up with more accurate approximations to pi, right? So it's quite important. It's quite a useful idea. This we can use certain approximations, like with this binomial, to find approximate values to certain numbers. Well, in this case, it's not particularly groundbreaking because all I'm said that 9 over 10 to the 4 is actually 9 over 10 to the 4. I've not really done anything impressive there. But I did this as an idea to lay the groundwork. What I find now instead of saying 9 over 10 to the 4, what if I then wanted to find 9 over 10 to the 10 power? Now, we'll have to rejig our expansion because now it's a different power, but we'd have to find many terms, right? 10 terms, or 11 actually. We have to find a lot more terms, so it's not particularly the most viable to just find all the terms. So what we can do then instead is just find a first few, right? So let's go back to our expand. Well, now it will be x plus 1 to the 10, right? If we were to then find the first few terms of this, right, of this expansion, let's say the first 4 terms, that would then be firstly 10 choose 0, x to the 0, of 1 to the 10, add 10 choose 1, x to the 1, and 1 to the 9, add 10 choose 2, x squared, 1 to the 8, and then x, and then 10 choose 3, x cubed, 1 to the 7, and then there'll be more terms after, right, which I denote with this triple dot. But there's more terms there, but there's going to be a lot more to calculate, so I'm going to leave it there. What I can then do, okay, that will go to then, well, 10 choose 0 is 1, x is 0 is 1, 1 to 10 is 1, so we get 1 first. Then 10 choose 1 is 10, so we're going to get 10x. Then 10 choose 2 is 45x. Well, 45, so 45x squared, sorry. Then 10 choose 3 is 120, so 120 x cubed, and there'll be more terms after, but I'm not particularly bothered. Right, okay. So I want to, well, I need to somehow find or sort of estimate the value of 9 over 10 to the 10. So again, the brackets are the same, right? So I can equate them together inside, so get 9 over 10 has to equal x plus 1, which therefore means x would again be minus a tenth, right? Same value if we solve it. So that's what I'm going to plug in then, with the same sort of idea, plugging that value of x into this expansion to obtain some sort of value for 9 over 10 to the 10. Okay, if I was to do that then, x is minus a tenth. If I plug that in, then then we'll get that x plus 1 to the 10 is going to be equal to minus a tenth plus 1 to the 10. Now that is going to be indeed 9 over 10 to the 10, right? So that's great. But then I've got these values now. As I said, we only did the first 4 values. Because we omitted, we didn't do the other terms because there'll be a lot of terms to calculate. What we can then do instead is say this is approximate. So 9 over 10 to the 10 is going to be approximate to these terms, right? So if I plug in x is minus a tenth here, then I'm going to get 1 into this expansion. I get 1 plus a 10, lots of minus a 10. Add 45 of minus a tenth squared. Add 120 of minus a tenth cubed. So that's going to be approximate to then, if I work that out in the calculator, that expression, 1 plus a 10 of minus a tenth. Add 45 minus a tenth squared. Add 120 over minus a tenth cubed. I actually get 0.33. There we are. Right, now how does that then compare? If I were to then put 9 over 10 in the calculator exactly, that's going to be equal to 0.34867 ... They're very, very, very close, aren't they? Now they're not exactly the same, sure, but it's a very good approximation considering we only calculated 4 terms. I think there are like 7 terms remaining we'd need to calculate in this instance. So it's a very good approximation, right? Very, very close together. Our estimated value of that expansion and the true answer, which was this, if we put it in the calculator, right? It's a very good approximation, and I should say as well, this is actually an approximation which we call, by the way, this symbol, this double squiggly line, means approximate to. Another bit of notation. So it's like an equal sign, but it's not exactly equal. It's close to. But it's only approximate to because we're not including all the values in the expansion. So when we're substituting values of x in, because there's only 4 terms we're using, not all the terms, it can only be an approximation. It's not going to be the exact answer. But the answer we got, which is again approximation, is very close to the actual answer. Okay, so that's where estimation comes into play here, where we can estimate quite well, actually, particular certain values of interest, like 9 over 10 to the 10, quite awkward numbers, right? With an expansion to get a very, very good approximate answer, which is very good for particular fields where you've got all sorts of numbers and you need to approximate. You're not interested in a proper, like, exact solution, but you need a very decently close solution nonetheless. But this is where this comes in handy. Now suppose instead let's say let's actually take a value of x. Let's say x is minus 19 over 100. Might seem a bit random, but you'll see in a second. Well, then that means the bracket x plus 1 to the 10 would then be minus 19 over 100 add 1 to the 10. Now that would be then 81 over 100 to the 10. Hopefully you realise then that the 81 over 100, well, that's actually just 9 over 10 all squared, right? To the power 10. I can switch that around to say 9 over 10, 10 all squared as well. I can switch the indices around. But there we are then. Well then, if I found the expansion then of this, well, this is 9 over 10 power 10 all squared, right? So then I can just square root the answer, right, at the end. So then what I'm going to do then is sub x is this value of x minus 19 over 100 here into my expansion. Now this would get this result, right? That of 9 over 10 to the power 10 all squared. So then that's going to be approximate to, then if I recall my expansion, so it's 1 plus 10x firstly, so 1 plus 10 lots of minus 19 over 100. Then add 45x squared, so 45 lots of minus 19 over 100 all squared. And then add 120 of minus 19 over 100 all cubed. If I put that in the calculator, then I would get that this is well, this is minus 0.09858. Okay, but then this is 9 over 10, 10 all squared. So to get that 9 over 10 to the 10, well, I need to square root it. But obviously we've got a negative, we can't square root it. But in this case, actually, I only just need like the actual number. I don't need the plus or minus. I don't need to care about the sign. So this is just going to then be the root of 0.09858, which is going to be the root. If I put that in the calculator, 0.31397. There we are. I'll cut it off there. There we are. And now that value 0.313, that's still fairly close to 0.348 something, right? That's the actual value of 9 over 10 to the 10. Okay, so it's a fairly good approximation, right? But remember, when we substituted though, x was minus a tenth in here in this first example, we got 0.33. Now that's actually still closer to 0.348. Why are we getting different approximations? Let's investigate that. So if I recall the approximations, right, when x was minus 0.1, which is minus a tenth, the first one we looked at, the approximation was 0.33. Then the approximation we just seen when it was minus 19 over 100, which is minus 0.19. Then we got 0.314, right, effectively. And the true answer, 9 over 10 to the 10, if we put it in the calculator, was 0.3487 when we rounded it, right? So we can see the rough answers then. Now, as we saw, well, 0.33 here is closer to 0.34 than this one, 0.31, right? Now again, why are we getting different approximations, and as a result, can we find then a way to pick and find better approximations to the value? Well, actually, the answer to that is yes. But how exactly? Well, try and look at these numbers of x we picked then. When it was minus 0.1, we got a better approximation than when x was minus 0.19. Now, you can kind of, I guess, theorise then that 0.1 is close, ignoring the negative, right? It's closer to 0 than 0.19, right? If you imagine it on the number line, right? Number line here, minus 0.1 and minus 0.19. Well, 0.1 here is closer to 0, right? So then we could then think, well, actually, a smaller value a smaller value of x, an x that's a value that's closer to 0, gives a better, a closer approximation to the actual answer. So we can then kind of state this then, and we can see that a small value of x gives a better approximation, right? An approximation of the actual value of what we're looking for, right? We can see that 0.33 is closer than 0.314, right? So, and that's because 0.1 is closer to 0 than 0.19, it's smaller. And so what we mean by small value is, by the way, and you'll see this used in various parts of the course, when we say or refer to a small number is basically a number close to 0, right? That's all we mean. So again, if you think about a number line, and we don't care about negatives, just how close it is to 0, because think about a number line again. If, say, we had positive 0.1 and negative 0.1 and 0, well, they're the same distance apart, right? Obviously, one's negative and positive, but we don't care. The idea is that it's close to 0, ignoring any sign. That's what we mean. So if you have a decimal close to 0, it's a small number. And so if we have a small value of x, then we plug into our expansion, as we just did. A small value of x gives a better and closer approximation to the actual answer. So it's a better value to choose. So what this means is then is that actually if we have multiple values of x we can choose to substitute into, as we've seen here, we had two possible x values. We could probably think of more. X was 0.1, minus 0.1 and minus 0.19. Both of those we found a way to get an approximation to 9 over 10, right? But which one do we pick to give the best approximation? Well, it's the smallest one. So if we have multiple values of x, we choose the smallest one. To give the best approximation. So we can kind of think of ways to get smaller and smaller values of x to eventually get to better and better and closer approximations to the true answer. Okay. So yeah, and I've seen an exam question like that before, which is why I brought that up. Exam question asked, they gave you two values of x, basically what we've just done, and it said pick which one would give the best approximation, and then you have to pick the smaller one because it's a smaller number. Okay, so I thought to cover all the ground, to be detailed as possible, to cover everything, right? Because you never know. Okay, I kind of got the idea then, but why exactly is the smaller value the better option? So let me just remind the expansion we just did. 1 plus x to the power 10. This was the expansion, right, that we just used. Okay. Right, okay. Now, think about an expansion like this. In general, an expansion gives a polynomial of x, right? It has powers of x that go up, right? So we go from x to x squared to x cubed and so on. So then the next terms will be x to the 4, x to the 5, and so on to x to the 10. Right, okay. But what I then want to think about then, small values of x then, what happens when we raise it to higher powers? What if, for example, we had 0.1 to the 4 and 0.001 to the 4? 0.001 is smaller than 0.1, right? It's closer to 0. But let me just put them both in the calculator. Well, 0.1 to the 4 is 0.0001 right? And 0.001 to the 4 is 0.00000000001, I believe. Yes, okay. And hopefully you can see one is far, far more smaller and insignificant than the other, right? This one is basically zero than compared to this, right? There's so many more zeros. What that means is then that higher power, if we raise a small number like this to a high power, it basically goes to zero. So the smaller number we pick, the more insignificant the higher powers of x it is, right? So that means if we were to substitute this into the expansion, 0.001 compared to 0.1, it goes to 0 very quickly in this if we substitute into the whole expansion. And if we raise that, then say if we then raise this to the power 6 or to the power of 8 and then eventually to the powers of 10, well, you can imagine they basically go to 0 as we increase the powers of a small number. So that means then that the smaller the numbers we have, the values we have, the closer to 0 they are, their powers basically go to 0. They're basically 0, so they're basically contributing nothing to the overall answer. Which means then, if we needed to cut off all the extra terms after x cubed, well, as I said, x to the 4, or 0.01 to the 4 again, that's basically 0 here, right? There's so many zeros. And then imagine if you raise it to the power 5, that's going to be even more zeros. Basically, the higher powers of x then, for small value of x, will, like 0.001 here, will basically go to 0 and contribute nothing, and basically will not affect the answer. It'll be insignificant to the answer, which means it gives a better approximation as we need fewer terms to get a very close answer, right? And that's basically it. So the smaller value of x gives the better approximation because higher powers of a number, basically 0, it basically goes to 0, right? So we can ignore the higher powers of x. So because higher powers of a small number like this compared to 0.1, as you can see, there's a big difference. The smaller the number we pick, if we raise it to a power, it basically goes to 0. So it gives a better approximation, and we need fewer terms as well as a result. So there we are then. So effectively, all in all, at the end of the day, you need to know that if you have multiple values of x to choose to approximate something using a binomial expansion, we choose the smallest one, for the reason being to get the best approximation, because of the idea that high powers of a small decimal basically go to 0, so they don't affect the outcome. Basically means there's less error because it's not contributing as much. Because it's basically 0, so there's no error essentially. Anyway, and also talking about this approximation, if we then have small values of x, as we've seen, if we were to continue this expansion on, as I said, we would get powers of 4, powers of 5, and so on to powers of 10. Now, as I said, when x is small, as we've just seen, the high powers would basically go to 0, right? Well, that means if we're adding 0 at the end here, effectively, that's just nothing. So we can ignore it, right? So we can say for when we have a small number to plug in, the expansion approximates to the first few terms. So we can cut off all the extra terms, and we can say it's overall approximate to 1 plus 10x plus 45x squared add 120 x cubed. So yeah, so we'll be seeing some examples talking about that as well, but we can approximate an expansion as well by cutting off the extra terms, and that's the whole idea of binomial estimation. The idea we can cut out all the extra terms especially with a very, very massive binomial expansion. Imagine if this was raised to the power of 100, right? That'd be a lot of times we have to compute, but if we pick a small value, we don't need all the extra terms. We can just focus on the first few because those are the ones that matter. So that's the whole idea of binomial estimation. The idea that we can cut out extra terms. We don't need all the terms, which allows us to give an approximation to something. Okay, so that's sort of the theory, I guess, behind it. For quite a fairly long introduction, but I hope it has helped. As I said, I tried to be as descriptive as possible to cover all the grounds. But that's the whole idea behind the examples we're going to be working with. This is the whole idea of binomial estimation. The whole idea is we pick small numbers to get a better approximation, and how we can use the brackets, if we equate the brackets together to find estimations to certain numbers of values, as we've seen in here. But we'll look at some examples then. Okay, so this question then, find the first four terms in the binomial expansion of 1 minus x over 4 to the 10. Right, so firstly asking just for the first four terms. So that's just going to be then equal to, well, firstly the first term is 10 choose 0. Then we're going to, the x part of minus x over 4 is to the power of 0. Then 1 is the power of 10. Then 10 choose 1. And then minus x over 4 will be a power of 1. Then 1 will be a power of 9. Then we're going to have 10 choose 2 minus x over 4 squared. Then 1 will be a power of 8. Then we're going to have 10 choose 3 of minus x over 4 to the power of 3. And then 1 to the power of 7. Now that's four terms, so we don't need to do any more. So we can basically use a dot 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 to say, well, the other terms are there, but there we are. So if you calculate these terms then on the calculator, right, simplify it. Well, 10 choose 0 is 1. Minus x over 4 to the 0 is 1 as well, because it's power 0. So we just get 1 first. Then 10 choose 1 here. 10 choose 1 is 10. Minus x over 4. So 10 times minus a quarter is minus 5 over 2. So we get minus 5 over 2x. Then we have 10 choose 2, which is 45. Then 45 times minus a quarter, sorry. And it'll be minus a quarter squared. That would then get the 45 over 16x squared. Then lastly we have 10 choose 3, which is 120 times minus a quarter cubed, and that will get me minus 15 over 8x cubed. And there we are then. So those are my first four terms. Cool. Okay, fairly standard. Part B then says use your expansion to estimate the value of 0.975 to the 10, giving you your answer to 4 decimal places. So again, it's very similar to what we talked about. So we need to use this binomial to estimate this value. But I noticed the brackets are, again, fairly similar, right? So I have a number to the power of 10, right? Well, what if I put both numbers equal, so that inside the bracket has to equal 0.975, right? So then 1 minus x over 4 is equal to 0.975. Then I can solve for x, because then that x value tells me what I need to plug into here to get an approximation. Cool. So if I solve this then, well, x over 4, if I add x to, well, x then, let me just do it all in one. Well, if I solve this then, well, x then, if I, actually no, I'll do it bit by bit. So minus x over 4, that's going to be 0.975 take away 1. That's going to be minus 0.025. Then if I times by minus 4 to both sides, I then get that x then is minus 0.025 times by minus 4. That gets me 0.1. Okay, so that's the value of x then I get. That will then, I can plug that into this expansion, because then, what was it? 1 minus x over 4 then, to the 10, that's going to be 1 minus 0.1 to the 4 over 10, which would be, well, 1 minus 0.1 over 4, indeed, indeed gets me 0.975 to the 10. There we are. So then I can use my expansion in part A. Well, actually, 0.975 to the 10 is when x is 0.1, right? So then 0.1 into this expansion here. Well, 1 minus 5 over 2, lots of 0.1. Then plus 45 over 16 of 0.1 squared, minus 15 over 8 of 0.1 cubed. So then that would go to, if I put all that in the calculator, 1 minus 5 over 2, 0.1 plus 45 over 16 of 0.1 squared, minus 15 over 8 of 0.1 cubed. That's 0.77625. To 4 decimal places then, that would be then 0.7763 to 4dp. There we are then. So that's the whole idea, right? We can substitute values of x in, sort of equate the two numbers together, right? Set the two brackets together to get a value of x, which will then plug into the expansion to obtain an approximation. And like I discussed then, we could plug in multiple values of x to find the same thing. Then the smallest value of x, the value of x that's closest to 0. Say if you had 0.001 as well, another number we could try. That would give a better approximation than 0.1. Okay, but I've not asked for that here. But I thought I'd explain. I'd reiterate. There we are. Okay. Let's have a look at some exercises. So it says if x is so small, remember small means it's close to 0. Remember, as we discussed. If x is so small that terms of x cubed and higher can be ignored. So again, if we have x cubed and then x to the 4 and then any powers of x above it, then if it's close to 0, say 0.001, if we raise it to the power of 3, or to the power of 4, or to the power of 7, or so on, that would effectively go to 0, so we can ignore it, okay? But so that's the idea behind this. So ignore any terms of x cubed or higher. Show that then 2 plus x of 1 minus 3x to the power of 5 approximates to 2 minus 29x plus 165x squared. Okay, so it's pretty similar to some of the examples we saw last time with double brackets, and we needed to expand that. Well, again, this bracket on the left, 2 plus x, I can't expand or simplify anymore, but this I can. It's a power of 5. I can use binomial expansion. However, I only want all the terms up to x squared. I don't want any powers of x cubed or more, right? There's no x cubed term. That means then, in my expansion, I really only need the terms up to x squared, right? And so therefore then, if I was to expand 1 minus 3x to the 5 up to x squared, okay, well then that would be 5 choose 0, and then the x part is minus 3x to the power of 0. Then 1 would be a power of 5. Then we would have 5 choose 1 of minus 3x to the power of 1. 1 to the 4, sorry. Then 5 choose 2 of minus 3x squared, add 1 times by 1 cubed. There we are then. So I put all that in the calculator. Well, 5 choose 0 is 1. Minus 3x with 0 is 1 as well, so we just get 1. Then 5 choose 1 is 5. 5 times minus 3 is minus 15. So we get then minus 15x. Then the next term, the x squared term, well, if I choose 2 is 10. 10 times minus 3 squared is 90. So I get plus 90x squared. So there we are then. So that's that bracket then, right? So then I get 2 plus x, 1 minus 15x plus 90x squared. Then that goes to, that would go to then we need to expand it, right? So if we were to expand it, well then 2, first of all, again, needs to multiply by every term in the other bracket. So 2 times 1, 2 times minus 15x, and 2 times 90x squared. That would go to 2 minus 30x plus 180x squared. Then I need to do the same for the x part here, the next number here. So then it'll be x times all the terms again. Well, x times 1 is plus x. X times minus 15x is minus 15x squared. Then we have x times 90x squared, that'd be plus 90x cubed. Right, okay. Well, we can collect like terms. So to simplify, well, we're going to get 2. And then we have minus 30x plus x, that's minus 29x. Then we have 180, that is 180, my handwriting. 180x squared minus 15x squared, that's plus 165x squared. But we also have a 90x cubed. Now, they told us to disregard or ignore or get rid of, or don't put in x cubed or higher, or powers higher than 3. So we basically then can say this is approximate to 2 minus 29x plus 165x squared. And there's our answer. That is the answer there. So yeah, so again, remember, we can disregard high powers of x, because if x is small, so it's close to 0, it's a very small decimal, raising that to a high power would basically make it 0. So we can get rid of high powers of x for that reason. But all they told us in this case is ignore x cubed or higher. So if we get rid of that, literally we just get this approximation then. Cool. And so yeah, in questions like that, if they ask you to expand or only give certain powers of x, if you get any powers of x higher than that, you just get rid of it, ignore it, right? But anyway, so have a look at this question then. So we are told f of x is 1 minus 5x to the 30. First of all, find the first four terms of x. Fairly standard then. So 1 minus 5x to the 30. The first 4 terms then. So it's going to be 30 choose 0. Then the x part is minus 5x to the power of 0. Then we're going to get 1 to the power of 30. Then we're going to get 30 choose 1. Then we're going to get minus 5x to the power of 1. Then 1 will be a power of 29. Then we're going to get 30 choose 2 of minus 5x squared. And then 1 to the power of 28. Then we're going to get 30 choose 3 of minus 5x cubed, and then 1 to the 27. Now those are 4 terms, so we can leave it there. So the remaining terms we don't care about, so there we are. So then if we were to work that out then, so 30 choose 0 is 1, minus 5x to the power of 0 is 1 as well, so we just get 1 first. Then 30 choose 1 is 30. 30 times minus 5 is minus 150, so minus 150x. Then the next term, the x squared term, well, 30 choose 2 is 435 times minus 5 squared is 10,875 x squared. Then lastly, 30 choose 3 is 4060 times minus 5 cubed. I get minus 507 500x cubed, and then dot dot dot, right? But those are my first four terms then, right? There we are. Then part B then says, use your answer to estimate the value of 0.995 to the 30, giving the answer to 6 decimal place. Okay, so again, a similar sort of case, we need to approximate a certain value. Now again, notice the two brackets are equal, the same power 30. So to make them equal, I can then equate them, right? So then simply 1 minus 5xn would have to equal 0.995. Then if I solve for xn, that means x is going to be well, zero point zero zero 0.001. Yes. Okay. There we are. So that's the value of x, and I'm going to plug into here. Cool. And hopefully you can see that this is I think this is a really good value of x to pick because it's very, very small. So this will give a good approximation, right? Again. So therefore then, 0.995 to the 30 is going to approximate to these four terms when x is this, right? So then I'm going to get 1 take away 150 of 0.001, add 10875 of 0.001. Then lastly, we're going to take away 507 500 of 0.001 cubed, and that's a squared there, sorry. And then put all that in a calculator. We get we get this 0.86036675. It said to give it to 6 decimal places. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's 7 decimal places. So that will then go to 0.860368 to 6 dp, because the 5 at the end here rounds to 7 up. Okay, cool. Then part C says, use your calculator to evaluate 0.995 to the 30 and calculate the percentage error to your answer in part B. Well, the first one's easy. The first part of it's easy. 0.995 to the 30 is simply, if I put that in the calculator, 0.86. I should probably give this a 6 decimal. I should probably give this a 6 decimal places as well to keep it consistent. 0.860384 to 6 dp. There we are. Okay, so again, very, very good approximation then, right? Very, very close together, which makes sense again because x is very, very small. It's very close to 0. So we expect it to be a good approximation. Okay, but it says then to calculate the percentage error. Now, the percentage error then, I think you would have done it in GCSE in either science or maths, I'm not sure. But the percentage error is defined to be the estimate or the approximation minus the actual answer divided by the actual answer times by 100 to get it as a percentage. What this tells us then, that the estimate over the actual, you can do it either way around. If you get a negative, that's fine to make it a positive. But what this is saying is, as a proportion of the actual answer, how much of how far apart are we from the answer effectively, and as a percentage, that's what this is telling us. So this difference then at the top is giving me the how close they are, what the difference is between our estimate and the actual answer, and then out of the actual answer tells me basically how much error there is, right, percentage wise. There we are then. So then our estimate then was this, right? So that's going to be 0.860368. That's my estimate. Take away the actual answer, which I did on a calculator, of 0.860384, over the actual answer again, which was 0.860384 times by 100. If I put all that in the calculator, then I should get the percentage of. That's going to be a lot of stuff to plug in here. 0.860368. Okay, I get negative 0.00188 percent. Okay. Now, again, if it's a negative, I can just get rid of it. I don't really care. But I guess I should round it. Let's say to let's say to 4 decimal places, shall we say? So therefore, percentage error is 0.0019, right, percent to 4dp. Okay, there we are then. So again, very, 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 very small percentage error, which is what we like. We like estimations that are, very good at estimations, right? And we can make an estimate good by picking a small value of x to approximate it to. I'll keep drilling that in. But yeah. Okay, cool. Let's have a look at this question then. We are told a microchip company models the probability of having no faulty chips as P, no fault, equals 1 minus P to the N. Okay. Now this P, by the way, means probability. Okay. So this is saying probability of no fault. Okay. When we look at if you haven't looked at stats yet, all the probability part of it, you'll see that notation there. But for now, this P means probability of. Okay. So it's saying the probability there's no fault is this expression here, 1 minus P to the N. Right. So P is the probability of a single chip being faulty, and N being the total number of chips. First of all, then, it says state why the model is restricted to small values of N. So again, it's going back to the idea of small values being close to 0, right? So it means it has to be close to 0 to give a viable, a proper approximation, right? So therefore our answer is going to be small, because small values of P give a valid. Right, a valid mean obviously a good, like an actual proper approximation. A valid, good approximation. There we are, which is what we discussed earlier, right? Okay. Okay, part B then says, given that n is 200, find an approximate expression for P no fault in the form of a quadratic, right? A plus B, P plus C, P squared. So we're given n is 200. Let's just substitute that in then. So 1 minus P of 200 then. Now that is again equal to P of no fault. So we just need to evaluate this, expand it. Now, where do we expand it to? Because there's too many terms here. There's 200, right? But we told us a hint here. The expression needs to look like a quadratic, meaning the highest term has to be a quadratic term. So we only go up to the p squared term, right? So that's going to be then p choose 0, no, 200 choose 0, sorry, of minus p to the 0 on 1 to the 200, and 200 to choose 1 then, of minus p to the 1, and then 1 to the 199. Then the next term is 200 choose 2 of minus p squared, and then 1 to the 198. Now that's it though, then that's it, that gives me a quadratic term for p, right? P squared. You can see that here again because my answer only has 3 terms in it, right? So I only need the first 3 terms. Right. So if I just evaluate all that then, so 200 choose 0 is 1, minus p to the 0 is just 1 as well, so we just get 1 first. Then 200 choose 1 is 200, minus p to the 1 is just minus p, so we get minus 200p. Then this next term, 200 choose 2 is 19,900 times minus p all squared, but minus p times minus p is positive p squared, right? So that'd be positive 19900 p squared. And there we are then. And then add dot dot dot. And there we are then. And so the approximate expression then, so that's approximate to just these terms, right? So it's approximate to 1 minus 200p, add 19900p squared, and there's no more terms after it, right? That's the approximation. Cool, okay. Then part C then says the company wants to achieve a 92% likelihood of having no faulty chips on a production run of 200 chips. Use your answer to part B to suggest a maximum value of P for this to be the case. So, right, it's talking about a 92% likelihood of no faulty chips. That's telling you the probability. Did I spell that right? Probability has to be 92% or higher, right? Or more. Because if it's 92% likelihood or higher of no faulty chips, then that's what they want, right? So that corresponds to probability of no fault, right? Has to be has to be equal to 0.92. So that means then if probability of no fault is 0.92, then that means 1 minus p to the 200, right? It has to be equal to 0.92 as well. Well, we worked out the so it says use my answer to part B. Well, my part B is this expression here, right? So if I want 1 minus p to the 200 equal to 0.92, then that means I need to set this quadratic equal to 0.92. Right? Well, actually then, is this not just a quadratic equation to solve for p? So then 19900p squared, take away 200p, then 1 take away 0.92 is 0.08. So plus 0.08 equals 0. So then we can solve that via the formula, the quadratic formula. So p will then equal positive 20 plus or minus the square root of minus 20 all squared. Take away 4 lots of 19900, 0.08 over 2 lots of 19900, and then if I put that in the calculator, then that would get me okay, I get these values. So p is either 0.00963 ... or p is equal to 0.004 417 dot dot dot. Okay. By the way, I should say, if you did put that in your calculator, you would get your answer in standard form. That's that. If you get a small enough decimal, the calculator will give it in standard form. I'm not entirely sure if you can convert it to sort of normal decimal form like this, but you do need to be able to convert between standard form and normal number form, right? Which you looked at in GCSE. But there we are. So those are the values then. Now, which one do we pick? Let's have a look at the question then. What does it tell me about P? Here, it tells me that also P has to be less than 0.001. So that means then P is less than 0.001. Well, this is basically 0.009. That's going to be bigger than that, so we can't take this first solution. But this is 0.0004. Then that is bigger than 0.001, and it's smaller than, sorry. So we take that one. So therefore, P is equal to 0.000417, which is, does it say to round it to anything? No, so let's round it myself then, which would be 0.0004 to 4 decimal places. Okay, cool. Okay, let's move on to final exam question then. So this one then says, find the first 3 terms in ascending powers of x for the expansion of 2 plus 3/4 x to the 6. So it only wants the first 3 terms. So firstly then, very straightforward. That's going to be 6 choose 0 firstly. Then the x part, 3 over 4 to the x. It's going to be a power of 0. Then the 2, the other number, is going to be a power of 6. Then the next term, 6 choose 1, 3/4 x to the power of 1. Then 2 to the power of 5. Then we're going to have 6 choose 2 of 3/4 x squared. Then 2 will be a power of 4. And so those are the 3 terms, right? So we don't need to do any more than that. So there we are. If we went then to work that out, well then 6 choose 0 is 1, 3 over 4x to the 0 is 1, so 2 to the 6 is 64, so 64 first. Then 6 choose 1 here is 6, 6 times 3/4 is 9 over 2, times by 2 over 5 is 144, so 144x. Then this last term here, 6 choose 2 is 15, times by 3 over 4 squared is 135 over 8 is 16, times by 2 to the 4, I get 135 x squared. Cool. So those are the first 3 terms then. Cool. Part B then says, explain how you would use your expansion that we worked out, right, to estimate the value of 1.925 to the 6. You do not need to perform the calculation, so it's asking to describe how you would do it, right, but not actually do the full answer. Okay, so how would you do it? Well, it's basically what we always did before, right, previously. Notice, again, that this number is a power of 6. This bracket is a power of 6. I can then equate the two together. So what I would say is then, you would basically solve 2 plus 3 over 4x equals 1.925 to get x is what? Well, if I solve this, well, 3 over 4x is going to equal 1.925, take away the 2. And then if I divide by 3 over 4, I then get x is minus a tenth. So minus 0.1. Well, then I can use my expansion then. So and then substitute this value of x then into this expansion to get an approximation for this value here, and substitute into the expansion to obtain an approximation to 1.925 to the 6. Okay, cool. So there we are then, that's kind of what they're looking for. Now, there is a bit of a technicality because they did say, oh, don't do any calculations. We kind of did do calculations to solve for x, but they need you to, but you always, they will need you to specify the value of x to substitute into. So if you can't work that out, then you do need to solve it, right, this equation. To solve the value of x that you would need to plug into here. When it says use your expansion to estimate, it's telling you what value of x are you going to plug into your estimation, into your approximation, sorry, which is what we've done here. So you need to specify what value of x you're going to plug in to your approximation to get that estimation, to your expansion to get your value. Okay, and that's it then. So hopefully you get the main gist then. So really the main idea is you solve with these sort of questions, solve to find the value of x. And what I mean is solve the brackets, right? The value of x to plug in to the expansion to find an approximation, right? Hopefully you understood what we kind of did here now with these examples. It's the same sort of idea, right? We have we need to we find an expansion of a bracket, then we can use the bracket to find a value, the value of a number by equating the number and the bracket together to get the value of x. Then we can plug that x into the expansion to get that approximation. And if we have multiple values of x to choose from, to plug in, you pick the smallest one. So i.e. the value closest to 0. To get the best approximation, right? And those are basically the two key details of this section, okay? So there we are then. So that's binomial expansion. So that's the end of this sort of chapter. So I'll see you next time.